let us continue. In order to be more familiar in the operation of MOSFET, let us first discuss the MOSFET construction principle and operation. Now, a MOSFET is a 4-terminal device having a source, gate, drain, and body terminals. In general, the body of MOSFET is in connection with the source. So they are connected. The body and the source are connected, forming a 3-terminal device only, such as field effect transistor. MOSFET is generally considered as a transistor and employed in both analog and digital circuit. MOSFET is widely used for switching purposes and for amplification of electronic signal in electronic devices. Let us try to be familiar with the symbol for the MOSFET. As you can see, these are the two types of MOSFET. This is N-channel. This is N-channel enhancement MOSFET. This is N-channel depletion MOSFET. So what are the difference between the two? As you can see here from this symbol, this one here for depletion type MOSFET, this line is straight without any cut. But here, the enhancement type MOSFET, there is a cut on this line. Okay, this is an N-channel MOSFET. Now, if we are not going to show this name, how can you identify immediately that this is an N-channel MOSFET? Very simple. I'm going to give you a technique. The technique is, look at the arrow. The arrow is entering, right? This is just a hint as a technique. Entering, that means this is an N channel because it's entering. Okay? Here it is a P channel because the arrow is pulling away. Pulling away. It's going away from the body. Okay? So this is how you can identify. Okay, this when I saw this arrow, P channel immediately. This is N entering, N channel. And how do you know it is enhancement? Enhancement if they are this line is divided into 3, and this line here is there is no division if it is a depletion type. The operation of MOSFET can be compared to a water faucet, right? Operation. Let's say the voltage source or the source of water pressure can be likened to applied voltage from drain to source, wherein it will establish a flow of water, okay, which is the reverse flow of electron from the drain to source. So from the drain to source, so that means from source to drain is the electron flow, and it is being controlled by the gate. Then the very interesting here is how are you going to control the gate, how the gate operates. Now, MOSFET can operate in the depletion mode and an enhancement mode. When there is no voltage across the gate terminal, the channel shows its maximum conductance. Whereas when there is a voltage across the gate, it is either positive or negative, then the channel conductivity decreases. So when there is no voltage, there will be what? Maximum conductance. We can have maximum current, right? So the current is flowing from drain to source. Look at the parts. This is an N-doped region, and we have a conducting channel in between. What about enhancement mode? When there is no voltage, the gate terminal does not conduct. So it's opposite. And here, when there is no voltage, the gate terminal shows maximum conductance. So it's opposite. When there is maximum voltage, then the gate terminal, in the gate terminal, then the device shows enhanced conductivity. What is that enhanced conductivity? Okay, let us just compare these two. This is a depletion type. This is an enhancement type. As you can see here, there is a conducting channel, and here there is no conducting channel. So this is the difference between the two. The major difference, the absence of channel between the two N-doped region is the primary difference between the construction of depletion and enhancement type, right? Okay, now let us try to go to other slides. Before we proceed with our analysis, let us remember the operation of a diode, right? When it is reverse bias, like I have a P channel and N channel here, I put a negative here, there will be a very thick depletion region, right? Depletion region, because reverse bias. For forward bias, the depletion region becomes small, allowing the current to pass. This principle is also applicable in the analysis of Mosfet. Now, in the depletion type region, as I've said, as discussed earlier, when there is no voltage, it is very easy for the current to flow, right? In this case, for the depletion type, when the VGS is equal to 0, ID is equal to the IDSS. This is already the saturation stage of the Mosfet, where it can flow a maximum current. And the ID is given by the equation, Shockley equation. ID is equal to IDSS multiplied by 1 minus VGS over BP square, right? Where IDSS is a drain to source current, from drain to source current, with short circuit connection from gate to source. From gate to source, there is a short circuit. BP is the pinch off voltage, and ID is the drain of the source voltage. Pinch off voltage, it is the time where when there is about a depletion region here on this area. Okay, let me discuss this one here. Pinch off. So when you increase VDD, right? This one here, VGS, will be more negative with respect to the drain. If it is more negative with respect to the drain, what will happen? This negative charge here will disturb this electron. So there will be, as you increase this one, there will be a depletion region that will form here, right? Until, if you increase this one, continue increasing until the current cannot flow anymore, then the current will be 0. In that case, before it happens, that point, that voltage, it's like a threshold voltage. That point where ID will become 0, that is called the pinch off voltage, right? ID is the drain source of current. The more negative the voltage VGS is, the smaller the current ID until it approaches 0, when VGS is equivalent to B peak. The more we make it negative, so when we are trying to increase this one, this portion here is connected to negative. This will be more negative compared to the drain. So when this is more negative, you are increasing, disturbing this one. There will be depletion region here. The current path will be, the width of the current of the channel will be, conducting channel will be small, right? To accommodate the current. Now, this is determined by this equation, the Schottky equation. Okay. Now, suppose we have here as 0. When VGS is equal to 0, we have a maximum current, which is already IDSS. That is when VGS is equal to 0. This is the plot of ID versus VGS. This is the saturation. This is the ohmic region here. This is the ohmic region. This is the cut-off region here on this side, cut-off, and this is the saturation region. Okay, in order for the Mosfet to amplify, to be used as an amplifier, it must operate as saturation. Okay, suppose that we continue to increase this one, and this VG will become more negative compared to the drain. What will happen? There will be a depletion region here. It will try to block the current. That point, that very point here, that's say this is this one, that it is almost touching the other side. That is the point of pitch of the B pitch of point. So here in this case, if this is 0, right? If we make it negative, okay, when we are increasing it, we are making it VGS more negative compared to drain. Okay. If we put, what about if we put a negative source here, a negative source? If we put a negative source here and we continue increase the negative source until, let us say, for example, negative 6, when it reaches this negative 6, there a current ID cannot pass anymore, therefore the current is 0, right? Like here, VGS equal to BP, the current is 0, which you can see from the table. But using this equation, let's say the current ID will be IDSS over 4. So this IDSS divided by 4. So this one here, what will be the value of BGS? So to calculate IDSS over 4 is equal to IDSS multiplied by 1 minus BGS over negative 6, which is the pinch of voltage square. Calculating for BGS, we have negative 3. As you can see here, after calculation at negative 3, you reflect it here, IDSS equal to 4. The same, if you substitute IDSS equal to 2, you will have this value. This is the reflected it here, almost 2 volts, 0.3 BP. Okay? So now, okay, and the more negative the voltage BGS is, the smaller the ID current. Until it approaches 0 when BGS equal to B pitch of point. Okay? So it means that when we make it negative, it tries to disturb the conductivity of this conducting channel. And if you disturb this conductivity, the flow of drain here will be limited, will be reduced. Okay? Where by definition, if it is 0, we have an IDSS condition, as you can see here, when BGS equal to 0. This is for the depletion. Let us have a review first before we continue. What is the significant difference between the construction of enhancement type MOSFET and depletion type MOSFET? What is the difference? It is the conducting channel, right? So which of the following is an N-channel E MOSFET? Okay, as I've described, it should be D, because N entering, and depletion enhancement type MOSFET because this is not a straight line, not a continuous line. Okay, this is the answer to this question. And in N-channel MOSFET biasing, what do you call to the voltage level BGS that will result in a significant increase in the drain current, right? What do you call to that voltage level BGS when the result of the significant increase in the drain current? Significant increase, this is what when BGS is equal to 0, right? In that case, it will result in IDSS. Okay? Okay, now, enhancement type MOSFET. Look at the construction of enhancement type MOSFET. Here, as you can see here, there is no conducting channel, right? There is no conducting channel. Now, what will happen here is that if we put a positive polarity of the gate, okay, this will repel all the positive, all the holes of this substrate. This is a substrate, right? It will push it towards the other side. And if that happens, there will be no holes here on the substrate and all the electrons will be built up here. As I increase BGS, there will be more build up on this portion. Okay? So, if I increase BGS, the current carrying capacity of this enhanced conducting channel, now this is an enhanced conducting channel. This is not a permanent conducting channel. This is just an enhanced due to the positive voltage here. Right? So, the higher the voltage here, the higher current it can accommodate. That is the operation. Look at here. The effect. Let us try to check the explanation here. The positive potential at the gate will pressure the holes in the P substrate along the edge of silicon dioxide layer to leave the area and enter the deeper region of P substrate. The result is depletion region near silicon dioxide insulating layers void of holes. So there will be no holes, only negative, only electrons. However, the electrons in P substrate, minority carrier, will be attracted to the positive gate and the accumulation and can accumulate a region near the silicon dioxide layer. The layer and its insulation qualities will prevent the negative carriers from being absorbed in the gate. So it will not be absorbed in the gate. So it will remain there. BGS, as BGS increases in magnitude, the concentration of electron near the silicon dioxide surface increases eventually and induce an N-type region that can support a measurable flow of drain source. So the voltage level of BGS that result in significant increase in the drain is called the threshold voltage. It's given by the symbol VT or VGS threshold. So now, as I increased it, let us just again close this one. Let's say we started from 0. I have a very small voltage here. So it will just push this one, and your layer here will be very, very small. Right? It's not sufficient to conduct a current. If I increase it, it will become wider and wider and wider, and then it will have a more current carrying capacity. But these electrons cannot be attracted totally to the gate because of the insulation here. So there will be more electrons here. The higher the voltage here, the more electrons here, there will be accumulation. The higher the current that it can accommodate, it will increase. Now, having said that, now if we have accumulated here, then how the current is being controlled? Now, here we have BGS, right? Here we have BDS. Here we have the voltage between BDG. Right? This voltage between BDG is the one that controls the flow of current. As you can see here, it's not equal. The thickness is not equal. Let us have a KBL on this loop. I will have minus BGS minus BDG plus BDS equal to 0, and then BDG will be BDS minus BGS. Now suppose that I have a constant 8 volt BDS, I have an 8 volt BGS value, and then I'm going to increase BDS from 2 to 5. So from 2, what's the voltage BGS? Let's say this is 2, this is 8. What will be the BDG? BDG is equal to negative 6, right? Negative 6. If this one becomes negative, if I change BDS to 5, and this is this 8, minus 8 will be negative 3. So what will happen? The gate will become, on that region, will become less positive with respect to the drain. So the gate on this region, this area will become less positive with respect to the drain. So that's why the thickness of this region will be reduced, controlling the flow of current. Okay? So again, let's go back here. What is that threshold voltage? Go back to the threshold voltage. So a threshold voltage actually here is the required voltage. It's like in the diode. The diode we require for silicon, we have 0.7. It's the required voltage to allow the current to pass through a diode, right? In this case, we require a voltage called a threshold voltage so that a current can start flowing into the accumulated region. This is called the threshold voltage. Okay? Now in this case, when we are increasing VDS, when we are increasing VDS, it becomes less positive with respect to the drain. The gate is less positive with respect to the drain. So until such time that it is very, very small, then that the current is just about to close. The gate, that means this one, the opening here is just about to close. It is the pinching off, the beginning of pinching off. That voltage will be the pinching off voltage. Now, let us try to analyze this current here, ID, the current that will flow here, is given by the equation ID equals to K multiplied by BGS minus BT squared. And K, by the way, is equal to ID on. It is the time. It is the current at on time, right? When the conducting region is conducting channel is on, able to accommodate the current. And BGS, and here is the BTS, BT, the threshold voltage. Okay, BGS is the gate to source voltage. So now, as you can see there, it's very, very clear here on this figure. If I have a small BGS, I can allow, my region is not that thick. Let's say this is my conducting region is just as thick as very small as this one. This is the width. So it can only accommodate this much amount of current, right? And if I increase BGS, the region will become thicker and thicker. Therefore, the capacity of the current is increasing. Okay? Now, what is the threshold voltage here? The threshold voltage is the level of BGS that result in significant increase in the drain current. It's called the threshold voltage. Okay? So look at here. This is 5 volt. This is around 2 volts. Here is around. Look at the significant increase in the drain current. And here is the what you call ohmic region. And this is the locus of the BDS saturation. Because this at this point, this is the saturation of the Mosfet. Okay. Now, drain characteristics of an N-channel type Mosfet is equal to BT is equal to 2B, and K is 0.278 to the negative 3 ampere per volt square. Okay. What is that K? K is the term, is a constant that is a function of construction of the device. So we have the equation for K. Let us apply here, taking the data from this waveform. We have ID on, which is, let's say, the maximum, which is 10 milliampere. What is BGS on, which is 8. And then, what is BT, the threshold voltage, which is 2 volts. It's given. So we will have here 0.278. This is equal to AA. Now, having this one, obtaining the value of K, we can rewrite the general equation for ID. ID is equal to 0.278 times 10 to the negative 3 multiplied by BGS minus 2B squared. So this is the equation now for ID. So if you have this equation for ID, any value of BGS you put here, you will obtain the value of current. Let's say if you want to substitute 6 volts here, you will obtain the new value of current. Now let us compare. Let us have a small review here as we compare the depletion region. There is a N channel here, and the operation is that when this is more negative, okay, it will control the conductivity of the conducting channel. Okay, if you put more positive here or more negative, it will reduce the conductivity of this conducting channel. This is the mode of operation. So the more negative the voltage BGS, the smaller the current ID until it reaches BP. When it reaches BC, ID becomes 0, like here. When it becomes BP, ID is 0. But when BGS is 0, ID becomes IDSS, right? So this is for the depletion. And now for the enhancement type, we have, as we make it more positive for an N channel, more positive, increasing it will increase this enhanced channel. So if we increase this, of course, the current carrying capacity will increase. Okay, and you need to remember here the threshold voltage. It is the voltage where there is a significant increase in the current. This is threshold voltage. Starting from VT, the current ID increases rapidly until it reaches ID on. Where is ID on? This voltage. And the voltage equal to BGS on, where it operates in saturation, right? Okay. Now, again, this is the equation, related equation for the depletion type Mosfet, Shockley equation. And this is the drain current calculation. ID is equal to K BGS minus BT squared. And K is determined by ID on over BGS on minus BT. So both Mosfet must operate in saturation in order to be used as an amplifier. Now, let us try to check the biasing. In our experiment, we are going to work on, this is a feedback configuration, enhancement type Mosfet. So in this case, BGS equals to BDS. BGS will be equal to BDD, which is the voltage here. BDD minus IDRD. You will have BGS. Okay? And this is how it has been graphed. Okay, the Q point, of course, this is the we the best amplifier point without any distortion. So let us go to the impedances, input impedance, output impedance, and the gain. So it will be this is the enhanced MOSFET drain feedback. So the input impedance will be equal to RF, the simplified equation, RF over 1 plus GM RD, considering that RD is equal to greater than or equal to 10 RD, right? So RD is bigger than this value. Okay, now for the Z out, RD will be equal, it will just be equal to the value of RD, considering the same assumption that RD greater than or equal to 10 RD. And the voltage gain, the gain, B out over B in, is also equal to negative GM multiplied by RD. But how to calculate GM? How to calculate GM? Well, transconductance is equal to 2K multiplied by GBS minus BGS TH. Or we can simplify this equation as 2ID over this is the BGS minus TH. Actually, this is over voltage. So BOB is the BGS over minus BTH. How did we derive on that? How did we arrive on that relationship? Let us try to see. Okay. GM, the transconductance, is related to change in ID over change in BGS. So if this is a differentiation, we can just take the derivative of this, having this equation, we will obtain 2K BGSQ minus BGSTH. But look at this one. This ID here, it will equal to 2K. So we can just simply GM is equal to 2ID, right? But this is square here. But this one is not square. So we will divide this one with BGS minus BTH, right? And this is the equation that we showed a while ago, which is equal to this one here, right? This is the similar equation. Now,